The last topic we're going to talk about briefly in this unit is the method of images. And so way back at the start, we said we had this method using our Laplace and our Poisson equations, and that was one of two methods. So this is going to be the second method that we can use. The reason that we're not going to spend as much time on this is that this is limited to the case of charges in the presence of conductors. So it's not quite as general as our Laplace and our Poisson equations. However, if we do have these conditions met, then it's oftentimes going to be easier to use this method of images to find all of these values of interest. So our voltage, our electric field, our electric flux density, and our charge density on the surface. So let's talk a little bit more about what our image theory is. And again, keep in mind, we're briefly going over a subject that we could spend a lot of time talking about. So from image theory, we're told that a given charge configuration above an infinite, grounded, perfect conducting plane can be replaced by three things: the charge configuration itself, its image, whatever that means, and we'll get to that in a little bit, and an equipotential surface in place of the conducting plane. So there's a lot going on in that sentence there, so let's draw this pictorially, and I think that's going to show a little better what we mean by image theory. So let's say we have some infinite conducting plane, so it goes on in this direction, and so here this is our perfect grounded conductor such that we have V equals 0 in our conductor. And so let's say we have a few different charge configurations that we're interested in. So maybe we have some point charge. So let me switch over to blue. So maybe we have some point charge, which is Q. Maybe we have some line charge over here, which has a charge density rho sub L. And we could also have a surface or a volume. Let's say we have some volume charge. And so let's say that's some spherical volume, which has a charge density negative rho V. So what our image theory is saying is that instead of considering that system, we can consider something a little bit different. So we're going to keep our three charges. So let's copy that. So remember, this is the first thing. So it's replaced by the charge configuration. So our charge configuration. So let's go ahead and put that down here. So we have our same charge configuration. And we're going to also have the image of the charge configuration and an equipotential surface in place of the conducting surface. So what we're going to have is some equipotential surface here where our conductor surface was. So this is our equipotential surface. So let's say V equals 0. And so what we have then is we're going to have image charges. And so our image charges are going to be equidistant from our equipotential surface. And the idea there is that if we have a positive Q on the top, we need to have a negative Q positioned such that if we're looking at this surface here, we have a zero potential. So similar thing for that line charge, we would have some line charge which is essentially just reflected about that equipotential surface. And the density is going to be negative rho L, because again, we're wanting to cancel out the effects from our positive rho L on the other side. So similarly over here, we would have some volume with a positive charge density rho sub V. So down here, these are going to be our image charges. And so there are two conditions that need to be met if we're going to use this method of images. So let's come down here and write those two conditions. So our first condition that needs to be met is that these image charges always have to be in the conductor. So the image charge, or charges, depending on how many we have in the system, must always be in the conductor. So we can't have our image charges coming out of the conductor. It just doesn't physically make sense with this method. So the second is that the image charges must be located in such a way that we have that equipotential surface, so it can be 0 or some constant value. And again, that's sort of, we've talked about that by having, for instance, our charges equidistant from that surface. There we go, let's get our size back. So the image charges, again, charge or charges, we can consider one or multiple, must be located such that the potential is 0. And so really it can be some constant, so long as it's the same along that entire surface. And because of that, of course, we call it an equipotential surface. And again, remember that represents our conducting surface in sort of the real physical system. And so one sort of interesting application area of this is ion beam physics. So what we would do is we say we have all of these charges which are approaching some metal surface. And so as maybe this charge is moving here, we would say we have some image charge of equal magnitude opposite value, so negative q, which is moving here. And so we could determine our electric field, our forces, our accelerations, all of that thing using this method of images.